Okay, now we can start. So, welcome all of you on this session about problems in distributed systems. So, during this today and yesterday, there were a couple of sessions dedicated to the same topic, and during my presentation, maybe some slides will be even overlap, but I will cover slightly different way and slightly different problems. So, my name is Andrii. I am from Ukraine, and temporarily I'm living in France. I hope that temporary. But I am a software engineer at Hazelcast, and also I am teaching several courses about distributed systems at the universities in Ukraine. And in my previous life, I was Java user group leader and organizer of several conferences, DevOps Ukraine, Java Day Ukraine, and others. But now they have been postponed for the good time. So. What about my talk and what is the Hazelcast? How many of you used or know something about Hazelcast? Oh, yeah, good. For other person, I will give a brief introduction what Hazelcast is and why I am talking about distributed systems. So Hazelcast previously, in the first day of its invention, has been invented as a distributed cache for database for fast data access. Most of you maybe use it as a distributed map, distributed cache, and so on. After several years, they were added a new data structure for distributed logs, distributed atomic reference, countdown log, semaphores, atomic logs, and so on. And on the top of this platform also has been introduced the real-time stream processing engine. What things you can do with it? You can specify the sequence of operations that deployed to the Hazelcast cluster as a graph of operations, and then you can plug in the source of real-time data. It could be Kafka stream, CDC data, something event sourcing, and so on. You can maybe read from the raw sockets. And this data will pass through the steps of transformation of this real-time processing engine. And after this, the result of this transformation could be put it again in a Kafka or any other things. And of course, we have the number of different clients that you can write the code and from which you can integrate with this platform. This is the basic architecture of our platform. To implement this, we have our own network primitives because we are not using any frameworks, no Netty, no Spring, no other frameworks. It is the pure Java. Maybe we only use JSON libraries for serialization, deserialization JSON as external dependencies. Other things are implemented from our team from the scratch. So we have our network primitives, our serialization, deserialization, and schema catalog. It's represented like YAML-like language, but not actually YAML. And because we have different clients from different languages, there should be some executable that could generate these schemas for different languages, C++, Go, Python, and so on. Besides this, we have our remote procedure call, sync-async implementation. Also have our concurrency primitives because Hazelcast was invented, started a long time ago, so there were no at this time Loom project and other nice stuff that we have today. That's why we invented our own similar data structure and concurrency primitives. On the top of this, we have a couple of different distributed data structure. Some of them are introduce best effort replication mechanism, like if you know the CAP theorem, it is A and P data structure that provides you more available availability than the consistency guarantees. And we have the Raft-based implementation consensus protocol that give you ability to use CP-based data structure. CP, it means we prefer more consistency than availability. And this is our core part of our platform. And of course, when we implementing this, we are constrained by so-called distributed system postulates, like the relative theory by Einstein postulates. The distributed system have the similar one. First, several of them are even repeated from this relative theory. For example, communication speed couldn't be faster than the speed of light. It is the top communication boundary speed, but we have no low boundary communication speed, so your message could be delivered in milliseconds, seconds, minutes, hours, next day. And in these conditions, your distributed system should be able to continue to work and not waiting some kind of acknowledgement from unresponsive or very or from not with the huge latency. Another postulate is time is relative. And you may know that there is no global time in the universe, and all clocks that we are used, it is relative. And a very nice description of this was yesterday by Jakub. He described what is the problems. We have with usually timestamps and time clocks in our system, so we couldn't use timestamps in most scenarios and most cases. And the last postulate, it is that you couldn't distinguish the network delay from the or network failure from the node failure. It is called FLP theorem, and for many customers it is frustrating. They are frustrating when they understand that it's impossible to distinguish two of these things. So in this condition, every distributed system should be implemented and take this into the account. And for this talk for today, I would like to describe what problems we have found, we or our customers have found in our Hazelcast cluster. And these problems related with replication, network, Raft algorithm, and maybe if we will have a time, I will talk about clients problems, communication with clients. And I will show these problems using our open GitHub tickets. So let's start from the replication. In replication, one of the tickets was that the state of job is corrupted after one of the members was forcefully shut down. So what is the job? What is the state of the job? What is described? Job belong to our real-time platform processing engine. And as I mentioned before, you can specify the sequence of operation that should be performed on the real-time data that, maybe not real-time, but the stream of data that comes from somewhere from the client side. And this operation and this transformation will be performed in a very fluent, described as a fluent API, and could be visualized as a graph of operations. And if you have the cluster of Hazelcast and you deploy your job to the cluster, you are able to partitioning the data and speed up the data processing by moving it in parallel on different cluster members. It is one part, and the another part, it provides also the reliability guarantees. For example, if one of the member will die, the state of the job shouldn't be lost because all job state should be snapshotted and replicated to another member. And with this part of this scenario, we had a problem. So the problem describes that during the forceful shutdown of one of the member, another member has incorrect state of the snapshot. So it means that the snapshot is not replicated correctly from the one member to another member. And the question why it is happened and how it is possible. So why? In our implementation, job state or snapshot of the job state, replication is based on IMAP. IMAP, it is a distributed Hazelcast map. It is good, very productive map, so it has a high level of throughput, but it has one big problem. It doesn't provide consistent level of replication. It is implemented as a best effort consistency. So it is belong to the so-called AP data structure. It is designed for availability, not for the consistency. And if you build your solution on top of unreliable core or unreliable data structure, you shouldn't expect that your solution should work in all cases. That we face it in our implementation. It means that if you are based your solution of such kind of best effort or AP data structure, you can only provide eventual consistency guarantees or even not eventual consistency guarantee, so your data or customer data can be lost. How it can happen, I will show you on a picture. So, for example, we have one client and another client. We have these three members in Hazelcast, and for this member, for Hazelcast 1, the Hazelcast 2 will be the replica or real-time or hot backup for the data. When the client writes some information to the so-called primary member, this information is replicated to the backup. After the receiving the acknowledgement from this backup, the primary Hazelcast 1 should send the client the acknowledgement that the write is okay. In this case, if the client to decide to read this data, it will be redirected to the primary member and can read the actual data. It is in the best case, like the best effort scenario that we could provide. But in distributed system, you should always consider the worst case. The worst case will be the next, that the write operation could not reach the backup member. But in this way, we anyway respond to the client that his information have been written to the Hazelcast 1, and in addition we send him some error message that this information is not correctly backup to the Hazelcast 2. And the client could take into account this error or couldn't take. But what happened if after this period of time this Hazelcast member 1 will die? It means that the client 1 receives an acknowledgement with some error message that the data has been replicated. But actually, if client 2 decide to read this data from the backup, he couldn't find this information. And if this client 1 is the job, Hazelcast job that I described before, and client 2, it is the new coordinator of this job. It means that the snapshot that should be backupped to another member of the cluster will be lost, and a new coordinator will start job from the maybe previous or corrupted state of this job, if it has previously have the snapshot, and if it's not, it will have no state to continue or restart the job. So it was our problem. Boom. What we can do for this? First of all, build your solution based on the top of reliable primitives. As I said before, if you take into the core not reliable something, you shouldn't expect that your solution will be reliable, or you should provide something additional stuff that makes this solution reliable, but in general it is more complicated than build your solution from the more reliable data structure. What we can use for this to increase the reliability, we can use majority write plus majority read. This approach is widely used, but we can do better, because it also could be the source of inconsistency. That's why MongoDB and Cassandra, in addition to the majority write and majority read operation, has the so-called linearizable mode. In Cassandra, you can specify it during the read operation. No, not in Cassandra. In MongoDB, you can specify it during the read operation. And in Cassandra, they have so-called lightweight transactions that use Paxos consensus protocol if you would like to be consistent with Cassandra. So your solution should implement something that gives you linearizable guarantees. And what is it? This is one of the consensus protocols. For example, it could be Raft, most maybe widely used for the current moment. Zapt, this is the Zookeeper protocol, or old known, well-known Paxos that is hard to implement. So if you would like to implement the consistent and linearizable data structure, you should definitely use some of this consensus protocol to give these guarantees. And this is a picture that describes what consistency level your system could have if you implement it in different way. The left part of this picture is well-known database isolation level from read and committed to serializable, and using the more strict isolation level, you know that you will have more problems with performance. So the more performance solution is uncommitted, if it will be really present in database. And the strictest one is serializable level. The same could be compared with consistency guarantees in a distributed system. The most consistent one is linearizable, and the most performant is eventual consistency that is somewhere under the button of this picture. Why this is the less performant solution? Because to implement this, actually you should execute all operations sequentially, and you should also execute it in a blocking way, waiting for some acknowledgements, and this acknowledgement should come from the majority of members of your cluster. That's why it is a very poor scalable solution and not very performant solution. But if you relaxing your consistency guarantees, you will be able to implement all your replication stuff in a more parallel way, and those solutions will have more performance, but will have less consistency guarantees. And you have seen that in this case you can lost your data. Choose is yours. What consistency level would you like to have in your system, and what of the consistency level is suitable for your business case? Okay, let's talk about the network. Network in a Hazelcast implemented in an async way. So all operations, all data structure that you would like to send over the network is sent in an async way and put it into so-called it is also our implementation in an outbound queue. So it is put it into the outbound queue, and then in a async way will be sent over the network. And on the another side, on another member, it will be collected in the inbound queue, and from the inbound queue, it will be taken and processed and executed if it is some of operation. What is the packets? Packets represent, encapsulate the payload. It could be some operation, it could be some data, or it could be some operation and data. And in this way, our Hazelcast network is designed and is work. And it was this tweet yesterday. You should care about, when we are talking about the network, you should care about that the network has two problems. Exactly one delivery, guaranteed order of messages, and exactly once delivery. So I think you should like or retweet this message, because I found very strange things. I've created this snapshot this spring, and today I've decided to view what number of likes it has. For the current day, it has this number of likes, and on the spring, it has more likes than now. So maybe some person decided to unlike this post, or maybe Elon Musk, when he rebrands Twitter, lost some of likes in the distributed storage. So we should put this count of likes on the same position. Okay. And yeah, and of course we have the problems with message reordering. And this is problem with message reordering is very strange, because it could split down our cluster in different parts, and the cluster would not like to join back if this splitting, after this splitting. What I am talking about, we have implemented our discovery mechanism. So a new member could auto-discover another members and could automatically join the cluster. For this, if the new member is added to the cluster, it starts sending so-called join requests messages. It has IP address of this member and a unique ID of this member. And this is part of code is implemented very simply and in very aggressive way. We are in while loop trying to send in a busy wait cycle. We are trying to send multicast service request with join messages. When this new member realizes that it has information about the master, we are stopping from this while loop, and it means that this member is successfully joined to the cluster. How it could be represented on the timeline diagram? So, in the following way, so it is existing two members, and this is the new one member that would like to join to the cluster, and it starts sending this join request. In some point of time, it realized that it's already joined to the cluster and stop it, but while it doesn't happen, it continued to resend this join request. And what can be happened if at this point of time, this member will be restarted? After they restarted, it will have the same IP address, but it will have the new UID message. And it continued to perform this join request work. So sending a new one join request with the new ID of this member. And in some point of time, it could join the cluster and it will be everything okay. But let's go to the message reordering. In some situation, it could be depend from different factors. The old one, join request, could be somewhere stuck in the buffers network, I don't know where, and could reach this Hazelcast member one after the new restarted member already successfully joined this cluster. And what will happen? The Hazelcast member 1 will consider the old join request as a new join request and will kick off this existing member and replace this existing member for non-existing one, the stale one. And in this way, cluster will be divided into several parts and will have no chance to join back. We should just start it in a whole sense. So why this is happened? This happened, boom. This happened because we couldn't detect the outdated messages. You couldn't detect that is the new message and this is outdated message, and we shouldn't process the outdated message. So what can we do for this? We can use timestamps, but from yesterday's talk, you should know that is a bad idea. So let's decide not to use the timestamps. And the best idea is to use some kind of the logical clocks and create a new field version that will be monotonically increased, and by this version you could distinguish what is the old one and what is the new one, cluster configuration or member or something like this. And using this we could ignore all stale messages. And another case that we are going with, because it was the easiest one, is we can save the list of disjoint members, and this solution is also help us with exactly ones or delivery guarantees or with idempotency guarantees. So it is a memory leaking solution, but good enough for the current moment. Okay, and network and out-of-memory exception. With this case, I will talk about this in detail a little bit later. We have a problem that is related that we have our outbound queue message queue that is unbound. And if another member is paused, this will be not detected by our failure detector. And messages, in addition with some retry mechanism, will be stacked into outbound queue. So how it will look like? This is our outbound queue. And since this member couldn't read messages from our queue because there is something problem, this member can be paused or something else. And this message will be stacked in this outbound queue, and some point of time, memory will be finished, and we will have the out-of-memory error. I will show you later how it's actually happened in our Raft implementation. So what we can do, we should use some defensive mechanism. And these mechanisms could be implemented on different levels. For example, we can reduce message packet size, but it is not the guaranteed solution because we could generate a lot of messages, with small payload. Another good solution is to introduce is to limit your retries. Your retries shouldn't be unlimited because in some point of time it will be the killer feature, and you will have out of memory or something worse thing. You should limit your buffers, queues, and apply someone drop policy. For example, if the queue is full or the buffer is full, you should drop new messages or drop the old one messages. But in this case, you should use retries to deliver at the end the dropped messages. So this policy with dropping messages should be implemented in combination with retries. Or you can introduce so-called flow control or backpressure behavior to not send new messages when you haven't accepted or received the acknowledgement that another part of your system already processed the sending. Actually, we have implemented for the current moment flow control mechanism because in our core, we use the unbounded messaging buffers for sending message. And to re-implement this stuff, we should re-implement the half of our platform. So we now decided to introduce the flow control mechanism. So it was some problems related with general stuff, and now I would like to continue with stuff related to the Raft protocol and and problems with his particular implementation. If you would like to implement your own Raft protocol based on the paper or master thesis of his author, you will face it that a lot of corner cases and even not corner cases are not well described in his PhD thesis. I will not go over each of them. I will only show you two problems. It is the slow followers problems and leader flip-flopping problems. So let's start from the leader flip-flopping. To understand this, about a small introduction to the Raft protocol. Raft protocol is a consensus protocol that provides you the strongest consistency guarantee. It can operate if you have the majority members of your cluster is available, and it provides automatical leader election and lock replication. During lock replication, you could replicate operations, data and operation in a consistent way. So the first step is leader election. Leader is elected by the majority of members. So to elect the leader, you should have, in this picture, you should have two members. It will be member itself and one of this, any of this member. The majority will be 2. So when the leader is elected, it starting sending the heartbeats to tell other followers that he is alive and he is in active state. And what happened if, for example, we lost connection between leader and this follower? This means that the leader couldn't send this follower the heartbeats and only could send heartbeats to this follower. After a couple of seconds, this follower will detect that there is no heartbeats from the leader, and as it designed in a Raft protocol, it should start the new leader election. It will nominate itself as a candidate, increase his Lamport logical clocks, it is the term 2, and send the vote request to another members. So the available member is this follower, and the candidate will send the vote request to this follower. This follower will receive this vote request and compare the term number 2 and term number 1. Because this term number is higher than the leader's term number, it decides that we have something happened in the network, and this is the new leader, and by design, it accepts this vote request and responds that he is okay, that this candidate will become a new leader. So we have the situation when we have the new leader, and what happened with the old one leader? The old one leader, by communicating with sending heartbeats to this follower, will recognize that the follower term is higher than the leader's term. And by design of the Raft protocol, the old leader should step down and increase his term number and become a follower. So, works perfectly, yeah? But the new leader should start sending the heartbeats again. It is okay that heartbeats reach this follower, but there are still problems with the old leader and the new follower, yeah? And in a couple of seconds, new the old follower will recognize that there are no heartbeats from the leader, and he will nominate itself as a candidate, and you will have so-called problem leader flip-flopping. Leader will be changing, and your system will be unresponsive because it will be continuously in the leader re-election problem. Yeah. The only solution could be if the leader will be this member, but you shouldn't be. But it is it is tricky how we can implement this. Why this has happened? Because the Raft protocol is not designed for such kind of network topology. And you should change in some way, maybe use some additional stuff to recognize that in this case, we shouldn't change the leader. This follower should not accept the vote request. But in this case, this candidate, this member, will be always starting the new elections round. So one of our customers had such problem, and the best solution that we decided is to provide the guarantee communication between all members in his network, because otherwise this protocol, Raft protocol, doesn't work. So it was problem with leader flip-flopping. Another big problem and our pain is slow Raft follower. What is it about? We have talked about the leader election, and let's talk about the log and operation replications. During the operation replications, client sends some operation or some data that should be replicated to the followers. And when the leader receives this request from the customer, it put this data in his log, but not accepted it because it is not still replicated, and it will be in so-called uncommitted state. After this, the leader should replicate this information, should data to another followers. If the replication is successful, followers send acknowledgement that they successfully replicate this operation. And when the leader receives the majority of acknowledgements, so majority is 2, leader itself and one of this follower, it could commit this operation, can execute this operation, send the response to the client, and also tell the followers that they could also commit and execute this operation. This works in a normal case, and everything is fine. But let's imagine that communication channel between this leader and this follower has a huge latency. What will happen in this case? In this case, the leader will send the same append entries request with the new messages. This follower will receive this message and send the acknowledgement. Since we have the majority of 2, this operation could be committed on the leader and send response to the client side. And what about this append entries? About this request, we don't care about it. Because for the protocol, it is enough that the majority of the members will accept this message. And Raft protocol guarantees that in some way this member will be reached the same state as a leader by replicating in async way his state. So this message could be paused or stuck in the network, but in some way it will be reached, if the network is okay, should reach this slow follower. And that's also fine. But what will happen if after this we'll send a new message? A new message for the follower, for the normal follower, will go as the usual one. So append request will contain only this message. But what will happen with the slow follower? Since the leader has no acknowledgement of receiving his previous append request to this slow follower, it should send to this slow follower the difference between his log and the slow follower's log. So the leader tracks the last messages that from which he received the acknowledgement from the followers. For these followers, it will be message C. And for this follower, the last acknowledgement was from member B, from message B. So in this way, the leader should send the difference between his log and the slow follower's log. And this append entries will contain 2 messages. And it's fine, it is OK. But what will happen if we have a lot of clients with high load and they sending messages in an intensive way? This means that we can have the snowball problems related with these slow followers. So somewhere in the network, and it is the good case, the worst case, if it is not a network, it is some internal buffer. These messages to the slow follower is stacked and waiting for consuming by the another member side, the slow follower. So in the network buffer, we have the number of append requests that contains all previous sending messages. And in some point of time, coming back to our previous picture, this packet will shows that this is the append entries message. This is another appended message with previous one. Then, and you have the out-of-memory exception that all members stacked in the outbound queue, and the problem is that it is on the leader's outbound queue, and the leader will crash with the out-of-memory exception. And to fix this, we introduced the flow control mechanism, and this is work fine, but I argue that you shouldn't only implement flow control mechanism. You should also limit your outbound queues, outbound buffers, and another stuff in your solution. What takeaways from this talk? When you're trying to implement some distributed system or use existing one, try to understand what consistency guarantees you would like to have, or your customers would like to have, what the case is needed. It is not very easy or even impossible to build more higher consistency guarantee based on the some kind of best effort solution. To provide the real consistency guarantee, you should implement some consensus protocol, some consensus mechanism. So it will be the huge investment into your project if you would like to do this. Think about message ordering, does it matter or not, and delivery guarantee, exactly one, at least one, at most one. If you implement at most one, you should use some kind of, and exactly one, you should use some kind of retries, but be careful with retries. Retries like drugs, in small doses it can help, but in large doses it can kill your system. It is a very nice article, very old article from Amazon, but it's nicely describes this problem. Take into account your network latency and different timeouts, and what is more important, test your system by introducing the artificial latency, by pausing and unpausing your VMs, It is very easy to do with virtualization and with Kubernetes or Docker infrastructure. And you can find, by introducing the network latency, you can find very interesting behavior. For example, this behavior we found recently in our system, that under the stress testing, so the maximum load, the maximum capacity that we could put in our system, introducing even the small latency could significantly impact your performance. So without the latency, we have such throughput, operation throughput, and by introducing it is not actually 1 millisecond, it is 3 milliseconds, because it is in one way and another way and to the client, but doesn't matter. In it, the throughput is less than 10 times than the without latency. So try to test your system by introducing latency. Maybe you will be also surprised, but with some kind of such behavior. And the final takeaways: read books. It is well-mentioned book, and less often mentioned books. It is database internals. So it is more described how different databases are implemented and what problems you should care about. Okay, thank you. Дякую. We'll be happy to answer your questions if we have one of them. Oh, perfect, no questions. Okay, thank you for attention. Have a nice conference.